So we are going to talk about two different cases of collisions. One is known as elastic collisions, and in elastic collisions, the kinetic energy is conserved, so the change in kinetic energy is zero. But in inelastic collisions, the kinetic energy is not conserved, and most usually the change in kinetic energy will be less than zero because the kinetic energy before will be greater than the kinetic energy after because some of that kinetic energy has been converted into heat. And in this video, we are going to be focusing on the case of the inelastic collision where the change in kinetic energy is less than zero, or at least not equal to zero. Okay, so let us look at two bodies in a one-dimensional collision. So we have a body m1 moving with some initial velocity v1 naught, and then another body m2 moving at some initial velocity v2 naught. And then after the collision, m1 moves with some final velocity v1, and then m2 moves with its own final velocity v2. So we know from a conservation of momentum video we had earlier that P1 naught must equal P final. So this is just the total momentum before the collision is equal to the total momentum after the collision. And we can write that as P1 naught plus P2 naught equals P1 final plus P2 final. And then we can drop the overhead arrows because the motion is one-dimensional, right? And then we're going to only use m and v and rewrite this as m1 v1 naught plus m2 v2 naught equals m1 v1 plus m2 v2. All right, so if we know the values for the masses and the initial velocities and one of the final velocities, then we can find the other final velocity. But now we're going to jump into a special case. So let's say that instead of having some initial velocity for m2, we're going to say that instead of having some initial velocity, we're going to set it to 0 meters per second. And here, instead of having m2 as a separate entity, we're going to say that m1 and m2 are stuck together with some final velocity, just v, like that. So that is our new problem, and this is what is called a completely inelastic collision. So completely inelastic collision just simply means that the two bodies have stuck together in the final motion, as we see over here. So the two bodies are stuck together with a common velocity. And this allows us to write m1 v1 naught, and we don't have a term m2 v2 naught, or we can just set it to 0 because we see that the initial velocity of m2 is just equal to 0 over here. And we can set that to m1 plus m2, because now that they're stuck together, we can sort of look at them as a singular entity with a common final velocity v. And rearranging gives us that v equals m1 divided by m1 plus m2 v1 naught. So if we know the values for the masses and the initial velocity v1 naught, we can also find the final velocity. All right, and know also that the final velocity must be less than v1 naught because the ratio of the masses, m1 over m1 plus m2, must be less than 1. That was how you find the final velocity or set up the system of equations for a completely inelastic collision system. So the key points to remember are that linear momentum is conserved. So delta P is going to be equal to 0. Right, and also finally, you're going to have m1 plus m2 as your mass times some v. So these two make the problem a lot easier for you to solve and find different velocity values, or maybe even m values depending on what you're given. So in the next video, we're going to be looking at elastic collisions, which is a little bit more complex, but really once you set up the equations, they're extremely easy to solve as well.